Hello everyone, welcome. In this video, we'll discuss the procedure for solving Bernoulli differential equations. But before we discuss the procedure, we first have to make sure that we are indeed dealing with a Bernoulli differential equation. The main characteristic of a Bernoulli equation is that it can be written in this form, which is very similar to the standard form for linear differential equations, except for the y to the n on the right-hand side. It's worth noting that sometimes your equation may not readily be in this form in order to obtain the y to the n factor on the right-hand side. Once we've verified that our equation can be written in this form, we next have to pay attention to the value of n, which is the exponent on the y. We need to ensure that n is not equal to 0 or 1, since if this were the case, the equation would just turn into a linear first-order equation, which is not a Bernoulli equation, and so the procedure presented here would not apply. The first step for solving the Bernoulli equation once we have it in this form is to take our n value and use it to generate v, which is always y to the 1 minus n power. Once we've done this, we can divide our differential equation by y to the n, and after making some simplifications, we see that we end up with a y to the 1 minus n power factor in our equation, which is the same as our definition for v. We can substitute in v, which means we are transforming our input variable from y to v, which means we should not have any y's present in our equation. Next, we see that we have the derivative dy dx, and since we want to write y in terms of v everywhere to avoid having more than two variables in our equation, we need to write this derivative in terms of v instead of y. We can do this by differentiating our definition for v with respect to x, and after applying chain rule on the right-hand side, since y is a function of x, we end up with the following. We see that we have now produced a relation for dy dx in terms of dv dx. We can isolate dy dx algebraically, and then plug it into our equation. After making some simplifications, we end up with the following. This strategy is advantageous since the resulting equation is linear and can be solved using the method of integrating factor. I've covered the procedure for the method of integrating factor in a separate video, which I will leave a link to in the description. Remember, n is not a variable, it is just a constant. So we can multiply the entire equation by 1 minus n, and then redefine the coefficient in front of the v and the right-hand side as p1 of x and q1 of x. Next, we could generate our integrating factor using p1 of x and proceed with the solution procedure for first-order linear differential equations. Let us consider the following example. We are asked to find the general solution of the following differential equation: y squared times dy dx plus y cubed minus e to the x is equal to 0. We should be able to somewhat immediately recognize that this equation is not a linear equation, since we have at least one y that is not raised to the first power. We can determine if this equation is a Bernoulli equation if we are able to write it in the following general form. We can move the third term to the right-hand side and then divide by y squared in front of the first term, and we see that we are indeed dealing with a Bernoulli differential equation since it can be written in the Bernoulli general form. Next, we could use this form to take note of n, which is negative 2, and then use it to generate v, which is y to the 1 minus negative 2 power, which turns out to be y cubed. Next, we could divide by y to the minus 2 power in our original equation, and we see that the second term on the right is simply our definition for v. This happens every time, so long as the procedure was applied correctly. We can then focus on transforming the derivative dy dx in terms of v by differentiating v with respect to x and applying chain rule since y is a function of x. After doing this, we can isolate dy dx in terms of dv dx and plug it back into our original equation. After doing this and simplifying, we obtain the following. The resulting equation is linear in v, and so we can solve it using the method of integrating factor. But we first need to put it in standard form, so we multiply the entire equation by 3, which means our integrating factor mu is simply e to the integral 3 dx power, which turns out to be e to the 3x power. We can then multiply the entire equation by mu, which is e to the 3x power, and as usual, the left-hand side of the equation can be written as the derivative of the product of mu times v with respect to x. I once again encourage you to watch my video on integrating factor, where I cover this procedure in greater detail. The link is in the description. The equation that results from this procedure is separable. We can solve this by moving the x's and dx on the right-hand side and allow the de to the 3x times v to remain on the left-hand side. We can integrate both sides. On the left-hand side, the integral of the lumped quantity de to the 3x times v is simply e to the 3x times v. On the right-hand side, the integral 3 times e to the 4x dx is simply 3/4 times e to the 4x plus c, where c is a constant that contains both integration constants from the left-hand side and the right-hand side. Let's not forget, we still need to substitute v in terms of y back into our equation. After doing so, we can isolate y cubed using some basic algebra, and then take the cubed root of both sides, resulting in the following final solution to the differential equation.